Here's a similar situation. Traveling around the corner, 115 kilometers per hour. So that's 31.94 meters per second. Now the car in front of me is traveling at 20 kilometers per hour. So much slower. That's 5.556 meters per second. And there's no room to pass him, so I've got to hit the brakes. That means I've got to have an acceleration that's going to be negative because I'm slowing down. To the right is positive, so I'm traveling to the right. That's the direction of my velocity, and I want to slow down, so my acceleration must be to the left. So that's a negative acceleration. So here's the other car at 450 meters, traveling at 5.556 meters per second. Here I am at the origin, x equals 0. This is x equals 450. And I'm traveling with a velocity of 31.94 meters per second. There's no room to pass. I've got to do this in such a fashion that I don't hit the car in front of me. So how am I going to do that? So I'm going to have an acceleration. It's going to be negative. So my position x1 equals 0 plus 31.94 meters per second t plus 1/2 acceleration times t squared. I don't know what that acceleration is. x2 is equal to 5.556 meters per second t. So unknown here, I don't know t, don't know the acceleration, I don't know x1, and I don't know x2. What I do know, I'm going to just not hit the car. So at that position, whatever that position is, x1 is equal to x2. The other thing I know is that since I am just barely avoiding the collision, at the time I'm just about ready to touch bumpers with the car in front of me. This is not obvious. You've got to really look at this problem and figure this out. Just at the time I'm about to touch the front bumper of my car to the rear bumper of his car, our velocities must be the same. And so I need to utilize that. Now I know what his velocity is. It's 5.556 meters per second. So my velocity, which I'll call v1, must equal 31.94 meters per second minus, well, let me say plus a times t. Now we know a is going to be negative. So I've added another unknown to this, but it really is an unknown. I know that that must be 5.556 meters per second. So I have 4 unknowns here, but I have 1, 2, 3, 4 equations. So I have a system of 4 unknowns and 4 equations. So let me write them out. So 5.556 meters per second equals 31.94 meters per second plus a t. Now x2 is 5.556 meters per second t. This is the position of the guy in front of me. Remember, he starts 450 meters ahead. And that's going to equal 31.94 meters per second t plus 1/2 the acceleration times time squared. And so if you look at these 2 equations, are basically this equation substituting in those values and this equation utilizing the 5.556 already. So I reduced it to 2 equations and 2 unknowns. So to solve this out, what I'm going to do is I'm actually going to look at this first one, and I'm going to say AT equals minus 26.38 repeating meters per second. Now that's going to seem really odd. Why did I do AT? But I'll show you. This becomes 5.556 meters per second t plus 450 meters equals 31.94 meters per second t plus 1/2 AT times t. And so then I substitute that into here, and I'm going to bring this over to here, and I'm going to get 450 meters equals 26.388 meters per second t plus 1/2 negative 26.388 meters per second times t. That AT is right there. And you see when I did that, I only have one unknown, and that's time. And so this right-hand side becomes 13.19 meters per second, t. And so t is equal to 450 meters over 13.19 meters per second. Again, I have meters divided by meters per second, which is meters divided by meters per second, which is meters times seconds over meters, which is seconds, which is good. I'm looking for a time, and I get 34.1 seconds. So that's how much time it takes for me to decelerate. So my acceleration is equal to minus 26.388 meters per second divided by 34.1 seconds, and I get negative 0.774 meters per second squared. And that comes from this equation right here. I substituted my known time into that equation to get my acceleration. And now where does this take place? Well, looking at the second car, because it's the easier equation, 450 meters plus 5.556 meters per second times 34.1 seconds, and I get 639 meters. There are other ways you could have solved this equation. This is just the easiest way that I could see. That comes with practice. You'll get that figured out in time. And I want to graph these two. Now my car starts at 0. This is time along this axis. Position here. The other car starts at 450, moving very slowly. So that graph looks something like this. Very small slope. Mine has a very large slope, but wait a minute, I'm not a straight line. Mine is parabolic. What my graph is going to do is it's going to be a parabola. It's not like this, because that would mean I'm speeding up. I'm actually slowing down. My parabola looks something like that. So it's an upside down parabola. Okay, so I just want to go over the calculus involved here. For those of you that have had calculus, you will follow along here okay. For those of you that do not have calculus, come back to this at a later time. So velocity is the derivative of position with respect to time, and acceleration is the derivative of velocity with respect to time. If I take this equation, I can rewrite it as a dt equals dv. And then, remember what you do to the left, you do to the right. That's more than just multiplication and division, addition and subtraction. If I take the log of both sides, that's a legal move. If I square both sides, that's a legal move. If I take the integral of both sides, that's a legal move. So if I take this equation and I bring the dt to the other side and then I integrate both sides, I get this equation here. So I can go from an acceleration, which is a function of time, to a velocity. Now when you integrate, there's a couple of options. You can integrate both sides and then come up with an indefinite integral, or you can give limits to the two sides of the integrals. Keep in mind this integral is an integral with respect to time. So you're going to integrate from some initial time, I've called t1, to some final time, t2. On this side, the integral is with respect to velocity. And so the limits of integration have to be velocities. Now v1 then must be the velocity at time t1. In other words, these limits must correspond to each other. They're not the same, because one's a velocity and one's a time, but they must correspond to each other. And so v1 must be the velocity at time t1, and v2 must be the velocity at times t2. And so when I integrate both sides, I get that. I can do the same thing with this velocity equals dx dt equation, bring the dt to the other side, and then integrate both sides, and I'm going to end up with that. So if I utilize that, and I keep in mind our constant acceleration, if the acceleration is equal to a constant, then I want to take advantage of those integrals. Specifically, I'm going to start with this one right here. So the integral of a dt equals the integral of dv. But the acceleration is constant, so it comes outside the integral. So I get a times the integral of dt equals the integral of dv. Well, let's integrate dt from an initial time I'll call 0 to a later time I'll call t. dv I'm going to integrate from some initial time, but my velocity at the initial time of 0 is v0. And then I'm going to have some later velocity v. But the integral of dt is just t, evaluated from 0 to t. Don't forget the a. But this is just a times t minus 0, which is just at. Up here, this is just v, evaluated from v naught to v. But that's just v minus v naught. And these are equal. So v minus v naught equals at. Well, great. Add v naught to both sides. And I get v equals v naught plus at. There's my velocity. And we've seen that before. But again, this is only valid because the acceleration is constant. If the acceleration is not constant, it's not going to come out of the integral. You're going to have to integrate whatever that function is. Remember, the integral of v dt was equal to the integral of dx. That's right here. But here's v right here. So v naught plus at, I'm going to put that in. So I get v naught plus at dt, integrate that, equals the integral of dx. I'm going to integrate from some initial time 0 to some later time t. That means I'm going to integrate from some initial position, which we call x naught, or x0, to some later time x. This is just x minus x naught. Here I get the integral of v naught dt plus the integral of at dt, again integrating from 0 to t, but v naught is a constant, so this is just the integral of dt from 0 to t, and a is a constant, it comes out, but t does not, it stays in. Integrate that from 0 to t. The integral of dt is just t, evaluate that from 0 to t, don't forget your v naught. A, the integral of t dt is just t squared over 2, evaluate from 0 to t, and this becomes, this first term is just t minus 0, so that's just t, so v naught t. This is just 1/2 t squared minus 0, so that's 1/2 t squared, plus a times 1/2 t squared, but that's going to be v naught t plus 1/2 a t squared equals x minus x naught. Add x naught to both sides, x equals x naught plus v naught t plus 1/2 a t squared. And that's one of your other constant acceleration equations. So that's where the constant acceleration equations come from using calculus. If you're not quite sure, I recommend you rewind, take another look at what I just explained, go over it slowly, write it down, and convince yourself. Do the integrals yourself.